So good afternoon, everyone. I want to thank you for joining us. We're now going to transition to the awards portion of our event today. It's a pleasure to have you here. Really appreciate you guys taking the time to come back to help us celebrate our awardees. If we haven't had the pleasure of meeting, my name is Nick Siciliano. I have the pleasure of serving as your Alumni Association president. My background is I'm a scientist like many of you by training. I earned my PhD here in 2015. I am the current CEO and co-founder of Victoria Biotherapeutics. We're a gene-edited cell therapy company here in Philadelphia with technology out of Penn Medicine. We're proud to say that we're about to file our IND for our lead program. I hope to be dosing patients later this year. So it's exciting, even more exciting to be able to do it here in Philadelphia with technology that was pioneered here in the city. So thrilled to continue my career in this wonderful place. So Alumni Day. Alumni Day is the highlight of the Alumni Board's annual activities. I want to again thank and recognize my fellow board members for the work that they've done for this event. Again, particularly Pooja and the Strategic Initiative Committee, which plans this day. We have altered the format a bit on what it's been traditionally to include a fireside chat, a little bit more of an interactive panel with our awardees. I hope that resonates and goes well here today. So I want to recognize Pooja and her work for kind of reformatting the day a little bit. I also want to recognize Lisa and the Alumni Awards Committee for the work that they've done, selecting tremendous awardees to celebrate. So couldn't be happier to be able to share in that today. And I also want to point out that this year we had the largest group of nominations for the Alumni Awards that we've had historically. So made it a very difficult decision. No, I'm just kidding. You guys were tremendous, so we're happy to honor you. I hope that continues. So again, the nominations for awardees, that's a really big, part of a way that our, all of our alumni can contribute to being able to celebrate each other. So it's great to be able to do that. And I'm excited to hear from our 2023 Alumni Award recipients. Hear them speak today, and as you'll hear, we're going to honor alumni who are using science to improve consumer products and packaging. We're championing STEM education and pioneering best-in-class programs for workforce development here in the greater Philadelphia region. And each recipient reflects credit upon the Alumni Association, the College of Life Sciences, and of course, Jefferson University. To begin our award presentations, it's my pleasure to introduce Dr. Lisa Ambrose-Lancey. Dr. Ambrose-Lancey earned her PhD here in molecular science biology in 2010. She's the current group vice president of client services at Lockwood. She served on the Alumni Board since 2018 and is the chair of the Alumni Awards Committee. Welcome, Lisa.
Good afternoon, everyone. I have the honor of introducing our award recipients today. And first, we'll start with our 2023 Early Career Alumni Award, which is being presented to Dr. Jeffrey Saunders. Congratulations. Welcome. Go ahead and say a few words.
Big surprise, and thank you for everything that the graduate school, Dr. Grunwald, and everyone else does. I mean, it's clearly amazing to come back and see the growth, the opportunities, and the future of science here at Jefferson. And I will just say, in a few minutes, I'll give you a little bit more about what I do and why I'm here. But to Dr. Grunwald's point about raising your hand and asking what you want to do at the beginning of grad school, I couldn't be further from what I would have ever imagined doing. So thank you again.
Next, I have the honor of announcing the 2023 Distinguished Alumni Award to Dr. Kristy McGuire. Congratulations.
Thank you, everybody. I also echo the sentiments that this is a real honor, and I will say some more in my presentation. I have lots of people to thank, including Arthur. So also want to echo, it is just amazing to see the growth of Jefferson, and in particular, the College of Life Sciences as a testament to Dr. Grunwald and his amazing team at a time when lots of traditional post-secondary colleges and universities are really struggling. That Jefferson is doing the opposite. Makes us all proud Jefferson graduates. So thank you.
Next, introduce Dr. Grunwald again to present our next award.
Thank you very much, Lisa. And one of the annual traditions of our College of Life Sciences as we celebrate the JCLS Alumni Day is to recognize a member of the JCLS faculty with the award of lifetime honorary membership in the JCLS Alumni Association. This award is made in recognition of distinguished service of the college by a non-alumnus faculty member. This year, we're pleased to name Dr. Peter Ronner, Professor of Biochemistry and Molecular Biology in Sidney Kimball Medical College and a longtime member of the graduate faculty of the College of Life Sciences for this recognition. Peter, would you please join me? And before we present the award, I just want to say a few words in Peter's honor. We are honoring Peter today in recognition of his long service and dedication to the university and to our college, both as an educator and in a number of administrative and advisory roles. Peter received both his BS degree in 1974 and his PhD degree in 1978 from the Swiss Federal Institute of Technology in Zurich in the field of biochemistry. Peter subsequently relocated to the U.S. and to Philadelphia to pursue additional training as a postdoc fellow and research associate in biochemistry and biophysics at the University of Pennsylvania School of Medicine. Following his initial academic appointments as instructor of physiology at Harvard Medical School, research assistant professor of biochemistry at the University of Rochester Medical School, and assistant professor of biochemistry and biophysics at the University of Pennsylvania School of Medicine, you see biochemistry running through here as a theme. We were finally most fortunate in recruiting Peter to Jefferson in 1994 as professor then of, you guessed it, biochemistry and molecular biology. We currently holds the position of professor as well as vice chair for education. Since 1997, Peter has also ably served as a member of the College of Life Sciences graduate faculty, primarily through our PhD program in biochemistry, structural and molecular biology, and engaged with the education and training of students across all of our MS and PhD programs. During her career at Jefferson spanning 29 years, Peter's been recognized for his many contributions to teaching, scholarship, and service across 3 colleges, including Sidney Kimball Medical College, the College of Pharmacy, and our College of Life Sciences, including numerous Excellence in Teaching and Teacher of the Year awards, as well as recognition for being a mentor to his fellow faculty and a model of professionalism for the Jefferson community. In addition to having a national and international presence, including serving as chair of the Association of Biochemistry Course Directors and his publication of a leading biochemistry textbook, his service to Jefferson has included innumerable roles as a member and leader of committees responsible for oversight of faculty development, our educational program curricula, for graduate school admissions, and is member and chair of many comprehensive exams and thesis committees for our graduate students. His service as instructor and course director encompassed a wide array of classroom subjects under the broad umbrella of biochemistry, especially in his own research field of metabolism, its mechanisms of regulation, and the impact on health and disease. This research interest is also reflected in his many peer-reviewed publications, book chapters and textbooks, and research grants in our own College of Life Sciences. His teaching included courses such as BI 550 Topics in Medical Biochemistry, BI 535 Advanced Topics of Metabolism, and GC 550 Foundations of Biomedical Sciences, which continue to be taught today. On a personal note, as Peter now moves on to his retirement from Jefferson after 29 years of outstanding service and educational leadership, I'm going to remember and miss most of all our many discussions through the years, ranging from philosophical aspects of education to practical aspects of our programs and course curricula. While these discussions ranged over an incredibly broad array of topics, the theme, the common denominator that always shone through those discussions were Peter's dedication to the highest quality of teaching and learning and to student success. Thank you, Peter, for all that you've done for university, our college, our fellow faculty, and of course, for our students. So in recognition of his outstanding dedication to and significant impact upon a generation of Jefferson students, including the College of Life Sciences, Please join me in congratulating Dr. Peter Ronner as we present him with the 2023 award of honorary lifetime membership on our Jefferson College of Life Sciences Alumni Association. Peter, welcome to the alumni. As a token of your wonderful service, this is for you. Would you like to say?
Thank you all very much. And it is, of course, very special to receive this award from my friend Jerry, who is an eminent teacher, as you well know, here at Jefferson. It's actually funny. For me, in 1978, I came to Philadelphia as a postdoc, and there was an authority here in this building in the Daniel Bohr Institute of Anatomy. His name is August Epple. He was a specialist on the pancreas of fish, and I came here to consult him. So I could never have imagined that I'd be here again 10 years later. And yes, I do like biochemistry. I feel very strongly that I was fortunate enough to make the right decision for my life. So thank you so much for the award. I deeply appreciate it.
Thank you, Jerry. Congratulations, Dr. Ronner. So it's my pleasure to introduce Dr. Sanders, who earned his PhD from Thomas Jefferson University back in 2013 from the Wickstrom Lab. I'll tell you a little bit about some of the exciting accolades in his career and the work that he does at Schrödinger. Dr. Sanders, what are yours?
Okay, so I'm going to talk about it. I actually think I've just gone backwards or forwards a little too much. What seems like a very large divergence from what we do at Jefferson, what was done at Jefferson, but I think you'll find that it actually fits in very well. So I'm not even going to read the title, but I think by the end you'll have a good idea. So what I did at Jefferson in Eric's lab was focus on computational modeling, specific genetic imaging probes for monitoring disease. This funnel, which is something I have to look at very often in slide decks, is looking at identifying targets, modeling them computationally by targets. Could be a receptor, it could be a soluble protein, it could be something, an mRNA or other nucleic acid, and then actually building, validating, and looking at what the efficacy is. And so Eric's molecular design lab, which I had a chance to visit beforehand today, which is still kicking and doing a lot of wonderful things. The idea is that you start designing computationally first before you go in and do experiments. And that's going to be a general theme of everything on now. So what I've done at Schrödinger, for those that aren't particularly familiar with Schrödinger, we're a software company that's been around for 30 years. This is not a pitch. It's more to understand what we do and how it really ties into today's themes. Where my contributions going from computational modeling at the molecular level to understanding and predicting how we design drugs, how we design therapeutics, and how we design materials and things that impact our everyday life. And a lot of this is really due to the advents in computational technology, horsepower. We no longer need these giant server racks to be able to do really fun, interesting simulations. We actually do it on a desktop computer like this one I'm standing right in front of. And where my contributions really come into play are the physics-based learning and machine learning. So, as a company, we're trying to move from computationally assisted. So you may, and this is a very old term, computer-aided drug design. We're now moving to computer-driven drug design, where we can use best-in-class physics-based methods that are grounded in biomedical sciences, a lot of the things that I learned here, to be able to de-risk and accelerate how you do drug design development, whether it's small molecule, whether it's an antibody, whether it's a PROTAC, degrader, or any other new technology that will come on the scene. The idea is that we can use simulation to do this, and we can do this at the accuracy level of doing experiments, except it's greener and it's faster. And because I always love movies and I probably didn't do enough of them when I was here, the idea is that you're computing what is the binding. So the potency, the first step in designing a drug, right? You have a target, protein target, or some other type of target. You need to understand what those energies are. There's a lot of fun physics involved. I'm not going to get too involved in it, but the idea is this is what you're doing in the background, and this is what you're actually calculating. And so the idea is that that's great. You might test a single drug and you might spend your lifetime working on a few different therapeutic candidates. The idea is that we want to be able to de-risk, screen, and accelerate hundreds of projects in a matter of months. And so this is a combination of looking at 1 billion plus molecules, whittling it down to a few thousand, running some fancy physics simulation, then using machine learning, right, all the rage right now, and then being able to optimize and enrich the candidates that you want to test. And so that way you can get to the clinic faster, right? You can help save lives faster. And I'll just give a simple example because I do want to keep this grounded in life science, and it is part of what my early contributions were. So we also have a pipeline. We're not just a software company. What I've worked on are some of the technologies that have helped drive something like our WEE1 inhibitor, which is still in preclinical phases, but is moving very far along. Just to get out of biochemistry, honestly, this is the first cell signaling pathway I've looked at in a long time, and I probably won't look at another one for a while. I know that's what everybody does around here. But the idea is that you want to inhibit something before going into mitosis. And the idea is that for tumorigenic cells, if you can catch it before it goes into mitosis and you can, cause mitotic catastrophe, you can shrink tumor sizes. This is really great. There are already drugs on the market that do this. AstraZeneca AZD1775 does this, but there are claims and questions about the selectivity. So you don't, off-target effects become a problem. So, again, in the fashion of everything we do, we looked at millions of compounds, or billions actually, and then you can whittle it down and you can synthesize things and get, viable candidates in like 7 months. Where my contribution early on in these technologies was really looking at how do we look at selectivity. So some of the other inhibitors and things we've designed have off-target effects. And so there are ways to look at this. You can actually look at the full kinome. You can do docking. You can look at estimated potencies. You can also do selectivity screening, right? So how do you minimize off-target effects while optimizing potency and keeping it the same? And so that's an FEP plus technology, all the fancy stuff I talked about earlier, where I did the initial validation for this and how this tool is being utilized and leveraged across every major pharma. I think I can say that without getting in trouble in the world. And so we're able to not only optimize, but to make it more selective. And I'll somewhat skip ahead to the important part is that, for pre-existing therapies that are in the clinic now, we've actually compared. And so if you stop dosing and look at tumor size with what is now will become the current standard, the AZD drug, you do see tumor regrowth after you stop dosing. Whereas with the one that was designed and started with a computational first approach, does not see any tumor regrowth. Okay, so that's probably the most life science, biomedical sciences I'm going to talk about. Now I'm going to, foray into a whole host of other things. And how it really ties in is that what I learned here, the guiding principles, the underlying technologies that were a big part of Eric's lab and still are a big part of Eric's lab. He still has MD simulations up on his screens as soon as you walk in, is that it's all grounded in chemistry and physics. And there's actually a lot of comparisons to what's done in the materials realm today that is common in life science, but is also seen more as we shift to renewable, sustainable alternatives to oil-based plastics, things we touch on everyday life, moving towards more sustainable bioplastics, which come from the life science realm. So I'm going to give you 30 seconds on composite materials. For those that have done collagen work or have worked with wood in any sort of biochemical or physiological sense, you understand what a composite matrix is. You have some stiffening material like a carbon fiber, or you have something like hydroxyapatite in collagen, and that actually gives you a very strong material, right? And so this may not make a lot of sense right away, but when you think about things that we might see, or if you get on a plane recently, are now made with composite materials. One, because they are more sustainable, especially as we move towards more bio-based materials, and also they're more efficient. So you probably didn't think you'd see some planes up here on today's presentation, but it's important to point out that composites and moving towards biomaterials are actually used in things like defense and commercial aircrafts like the Boeing 787. That's not the only one. This is the 380 or A350, whatever it is. And that these are materials that are lighter, use less fuel, and you can actually fly faster. So there's a lot of advantages to using that. And again, computational technology can help accelerate it. So the same design principles, the same ideas as doing drug discovery, where you have to optimize not just potency, but also solubility, toxicology, and also as a formulation, right, getting into something that you can deliver to a patient. These same design principles can be used in material design, something like the composites that end up on an F-18, the F-35, or the 787. And you may wonder why you would want to do this. And I'll show you in a second, but this was something that was developed in coordination with Schrödinger, myself as the main technical driver, and then also some of the composite engineers at Boeing and legacy SciTech carbon fibers, which is now Solvay, a very large specialty chemicals company. So why bother to do that? So when you need to actually certify a new aircraft, you need to do a lot of testing, similar to how you would test a drug in preclinical prior to going, to filing an IND, going to phase 1, phase 2, right? This is all about safety and efficacy. When you're designing a new plane, the FAA has a lot of stringent criteria that pretty much works the same, except that the cost to test and to train costs over $150 million per plane. So, the idea that if you could reduce how much time you actually have to do something like an ultimate wing bending test, where they actually bend the wings to see when they break, the idea is that you could test this computationally, and that would be something that has a lot more applications beyond just bending the wings of the airplane you might take to, Europe or California. And so there's a lot of physical properties and chemical properties that you can get out of this, things that may, strike some resemblance, like hydroscopic behavior, mechanical properties, and these are big drivers here, and also, the underlying chemistry. And so I don't want to spend too much time, unfortunately, on that. But that can also be applied to propulsion. So another area we were approached by was the Air Force Research Lab and the propulsion directorate probably 6 years ago to apply some of the same technologies for rocket casings, for heat shields, for spacecraft re-entering the atmosphere. And if you think about where that technology has come from, about 100 years ago now, we're very quickly approaching that. The first liquid-fueled rocket test was done by Robert Goddard in Worcester County, actually at WPI. They built a lab down off away from the rest of the campus because they were afraid he was going to blow up the whole place. And that's come a long way. So now we actually build really, really large apparatuses in the desert. So if they blow that up, they're not going to hit anything else except for maybe Edwards, which is down the road about 10, 20 miles. And they test things like strapping rockets that have gone into the some of the capsules for transporting astronauts to the International Space Stations, and some of the more private aerospace companies that have come online in the past few years. Our contribution, and this is a publication that came out now 2 years ago, it feels like yesterday, is actually describing the chemistry that you can use to design and predict the ultimate thermomechanical properties and moisture absorption properties of rocket casing and rocket foams. Which is really important because if you look at what happened with the Challenger explosion, right, everybody remembers the frozen O-rings and Feynman, giving that whole speech, I think it was to Congress about that. Well, what happened after the O-rings failed was that there is a fuel tank, all right, and that actually ended up ripping off, sending it off its trajectory and causing, the tragedy that was. So being able to design safer transport and also fuel management systems is something that's really important. And this is also being used for hypersonic, which is heavily being researched for defense now. Okay, so that's very far removed from life science. I'll pull it back in and talk about, something that people have probably seen if you haven't seen a rocket strapped to the side of a mountain and being tested. It's really loud. Consumer goods, right? So I always like to make the analogy, you hope you never have to see a therapeutic in your life. You never have to touch it and you have to see the vial. You never have to be injected with one. But for the total opposite, when you think about consumer goods, we touch them every day. Right. There are things you see on a grocery shelf, things you see in a department store. Most of them are sold for under $10. But they are some of the largest consumption of raw materials in the world, and also some of the largest waste generators. Just as an example, food packaging waste represents 40% of all waste, plastic waste that we generate. So as we, as a society grow, as the demands for food, especially thinking about global climate change, all of those factors, it's really important to think about how we can bring innovation and some of the things I learned here to a very interesting area that actually ties back very nicely. So I'm going to use one simple example. Again, I wish I had time to talk about 30 others, but we're going to keep it short. And it actually drags it right back into something like dermatology. So 30 seconds on hair biology, we really are focused on hair cuticles, because what happens when you wash your hair, right? So you have hair, it's got oil, it's got dirt on it. And what you do is you take a very viscous solution that has surfactants, it has polymers, more polymers if it's a conditioning agent, fragrance molecules, and you dilute it with water at about 40 degrees C. And then the idea is that those surfactants can pull off or roll out the oil or dirt, and that you have a dilution phase, and then you actually affect surfactant morphology in a very large way. And it's very finely tuned. It's been known for a while. And then you have conditioning polymers. So if we want to design, let's say, the next generation, right, because most surfactants, most of these polymers come from oil sources. And as we move away from this to meet sustainability goals, really to keep our planet in one piece, because it's going to be on fire if we don't do it, we have to think about how we could test these things to replace the same formula that you probably use for 5 years, 10 years, or 20 years. And just again, diving a little bit more into the biology. It's not just proteins that outline the outer layers of the cuticle cells of your hair. There's actually a fatty acid that's covalently linked called 18-MEA that affects the textural properties. Why am I mentioning this? It's important to think about when you damage your hair, whether it's through UV, age, distance from the tip to the root, or if you've had a perm, if you've bleached your hair, you've actually probably stripped some of that fatty acid off your hair, and you're now left with a highly charged surface that has very different textural properties. You can see that, how they interact. Why would I talk about all of this? Well, the idea is if we want to test, right, and we want to go from a simulation first perspective, we want to be able to build representative models. And so there's no crystal structures for these proteins. Go to AlphaFold and you'll see spaghetti, or what would be the native fold. They're generally insoluble. Proteins I'm talking about are keratin-associated proteins, which are actually lining the outer layer of your cuticles and the F layer of the epicuticle. So because experimental methods aren't very good at resolving what it looks like, if we want a model that's realistic, we have to build something, and simulation is the only avenue that we can really use to do this. And so we've built models. We've actually published this. This was published last month now. The model's been around for over 4 years. You don't get to publish as much when you have to deal with industry all the time. But the idea is that we can actually mimic the cell surface properties. Those are dead cells, but understanding how it behaves when you look at fatty acid absorption, water behavior, wetting behavior, all those other things. It doesn't cause cancer, so maybe it doesn't get as interest, but something we deal with every day. Then designing a whole platform around how do we simulate the new shampoo, how the shampoo behaves, building hair models that incorporate damage, right? Because we probably all have a little bit of hair damage here, whether we want to admit it or not. And then understanding a system that will give you that textural properties, right? So what happens when you wash your hair and then you rub your hair together? And so since I can't spend too much time, we actually built entire simulation platforms in collaboration with L'Oreal to look at this. So we can look at 2 hair surfaces together. We can simulate full formulations. These formulations are actually replacing traditional conditioning polymers that are made with oil to ones that are made from polysaccharides. So using nature as the way to wash your hair better and more efficiently. I'm going to end on food science. And I think that, most people in food science, because I think it's probably much more immature of a field compared to life science. It is life science. There's really no distinction. And I think that distinction and that line gets blurred more and more every day with how not only the direction that we're going, but the level of understanding and the level of rigorous scientific research that's being done. Most of your food is made from polysaccharides, terpenoids, flavor molecules, carbohydrates, and proteins, right? Milk and casein micelles are a really good example. You get into much larger scale emulsions, food products, whatever. Those are maybe something that's been processed, but the core components, the core ingredients are things that are found in nature. And I'd say are even becoming more and more found from nature as we move away from traditional oil-based polyolefins plastics. And then this is, I would say something else, and is very much diving back into the life science work that I did here, is you can take chemistry, you can take something like starch, right? You probably have starch in your kitchen at home. You can heat it, you can add water, you can dry it out, and you can get a glassy polymer. You can get a semi-crystalline polymer. You can get a gel-like behavior, and you can make all sorts of things like plastic straws, plastic utensils, to even thermoplastics. Not quite the same as the things you use in an F-18 because they're really like to take up moisture, but we can model all these effects. So thinking about taking more and more things that would have been made, oil or for the same method for the last 80 to 100 years and actually trying to use nature to replace it and to still keep those same key, in this case, thermomechanical and water activity properties. And, expanding that, right? So if we want to reduce our plastic waste, we need to think about candy wrappers. We need to think about other things and removing what is probably an addition, an existing multi-layered complex process that's very energy intensive to a bioalloy. And actually, Mars does this with Snickers in Europe, just not in the US for whatever reason. What I'll end on is the plant-based meat. And so maybe some of you have had an Impossible Burger here, Beyond Meat, or some of the other products, right? Why bother doing it plant-based just because of dietary restrictions or consumer preference? Well, cows are actually really bad for the environment. Ethical concerns aside, they're the third largest greenhouse emitter. They take up a substantial portion to cultivate. 25% of our land mass is used just for raising and cultivating cattle. And that projection, as we reach 8 billion people in the next 20 years, I think maybe less, is going to grow by 95%. This is completely unsustainable. It's not going to go away. And it's something we have to do if we want to have a planet in 100 years that we can still live on. One way to address this is plant-based meat. And why? It uses a lot less water, a lot less energy and resources, and there is no ethical concern of actually growing, plants and then using them as a source to make a burger. There's a lot of engineering and science that goes into this. Now you're talking about mixtures of things like proteins taking from plant-based sources. So one thing that is easily transferable is real biochemistry or human biochemistry to plant biochemistry. There's a few changes, but not too much. And what it boils down to, if you want to make plant-based meat that's really good, is a great replacement and things that the consumer will actually want to eat. There's a ton of challenges. I could spend another hour again talking about this, but really being able to process it, have it taste the same, look the same, bleed the same, and chew the same, actually turns out to be a protein folding problem. How you unfold the protein, what state it's in, how these isolate sources are processed, gives rise to the smell and also the flavor and the textural properties. So while it seems like an engineering problem up front, in reality, it is a biophysical problem or a biochemical problem dealing with how do we deal with a large number of proteins. In reality, most plant-based pulse seeds are one protein and then maybe 20% rest. But understanding how to actually build a materials-based system that, again, is using nature, using plants as a starting point. And so that's where the work at UMass that I'm focusing on now. And to tie it back to structural biology, because I know I'm probably going hard left compared to where most people thought I was going to give a talk. Understanding at a physiological level how taste and smell are perceived is very hard. And up until the last 6 months, we didn't even have experimental structures for the GPCRs that are olfactory receptors or taste receptors. They've just been ignored because they generally don't cause cancer. They don't, in some cases, they can be used as therapeutic target, but they're not often the first in line when someone writes a grant. So thankfully, there's been a growing interest in this area. And now that we have experimentally resolved structures, again, on the basis of excellent life science work, we can start to really understand not just how to build plant or bio-based alternatives for traditional materials that we use, but also bringing it back and tying it to a physiological response at the end of the day. And so this is things that we're interested in looking after. So just to end real short, I like to look at all the people that have really had an impact on me over the years. And this slide's probably not big enough to encompass everyone. The people that first started to really fall in love with science, really want to do it all the way back to my undergraduate days with Bill Royer at UMass Med, to my wonderful PhD advisor. I've never met a person who was more upbeat, passionate, honest, and excited about science. And, he's today talking about he's spent over 40 years looking for an oligonucleotide therapy that works. And he's just now, I think, on to something that will really be a game changer. And to have that enthusiasm for 40 years is really impressive. Some of my, commercial mentors who have been awesome in cultivating who I am now. And of course, my Jefferson, community, grad students are now all alumni, professional colleagues, and of course, another alumni, and my partner, Debbie, who's been nothing but a source of inspiration for me the whole way. So things I would say to take away and really have guided me. It may seem like it's all over the place, but it's really about learning how to learn. And I think Jefferson does an excellent job of teaching its students and everyone here on how to be independent thinkers, how to be analytical, regardless of the topic. I covered a lot of different things, but it's the same scientific method over and over again. It's all physics, biology, and chemistry, and we get an excellent foundation here. Other things, for future scientists that may be in the room, don't worry about titles. No one cares. Really, at the end of the day, everybody can contribute. And some of the best scientists I ever met have come from the most unlikely places. Of course, don't be afraid to it when you don't know something. You can see I'm all over the place. When someone says a word or jargon I don't know, I'll stop the conversation and say, I don't know what that is. And 99.99% of the time, people are really happy to talk about the research that they're working on day in and day out. Your perspective, your background, your personality are all key components as a scientist. I think we all have unique skill sets here, unique personalities, and unique, I would say, advantages to leverage those to be successful in everything we do, whether it's running an ever expanding graduate school program versus those of us that work at industry. There's a lot, and you have a lot to contribute. Always surround yourself with people that believe in you. That's one of the best things you can do. And I would say that despite, we work in different areas, we're all after the same goal. We want to make this place a better world, either whether it's through health, whether it's through better food, whether it's sustainable materials that will keep our environment from exploding. And last but not least, I think, from a perspective, I know it's like to be a grad student, most of us do in here in this room. Don't take yourself too seriously. Your mental and physical health are really important. It's more for the younger kids, although as adults, right, we all struggle with keeping deadlines and things to do. So, it's okay to take a break. It's okay to have fun and never take yourself too seriously. All right. And with that, thank you so much again for the opportunity. Not only I'm humbled by the award, but the opportunity to speak. I really loved it here. I have a lot of fun memories, and I can't wait to catch up with some of you later.
It is now my true honor to introduce a dear friend of mine and our Distinguished Alumni Award recipient, Dr. Kristy McGuire. I've had the pleasure of seeing firsthand the impact of her work in STEM education and workforce development. So I think you guys are all going to be really impressed to hear some tremendous accolades.
Thank you for that kind introduction. I'll have some additional words to say about Nick and others in the audience as I go through the presentation, of course. The title of my talk, and apologies because I just had to give a faculty seminar at the Wistar Institute yesterday. So this is a modification of that talk. Training a diverse and skilled workforce for the life sciences through engagement with authentic biomedical research. So as Nick said, I'm currently the Dean of Biomedical Studies at the Wistar Institute, but how did I get there? Some of you know that I did my bachelor's of science and biology at what was then Loyola College, but is now Loyola University, Maryland. And I also had the opportunity to participate in undergraduate research on carrot embryogenesis. I knew I wanted to combine science and teaching. So upon graduation from Loyola, I returned home to Philadelphia and started working on a master's in the science of instruction at Drexel University. But in order to pay for my master's degree, I got a job working in a human genetics lab at what is now Drexel University College of Medicine. And I actually loved this work. I was doing mutation detection in collagen and extracellular matrix genes in human fetuses. And I was enjoying the research so much more than the education courses I was taking that I decided to follow my best friend from Loyola College, Karen Schindler, who was a previous Distinguished Alumni Award, to Thomas Jefferson University. Karen had started the year before in the PhD program in biochemistry, but I decided to pursue a PhD in genetics and worked on mouse oocytes This is actually an image that I took. I spent a lot of time in imaging facilities, learned how to work a lot of confocal microscopes. But this is a meiotic spindle with aurora kinase A at the poles. 2 points about this. One, I've always been more interested in the next generation, embryos, fetuses, oocytes, than I was in currently what is going on. But that my experiences in the classroom and doing research in labs were really far apart. They were very separate at all of these institutions. My career path, and actually meant to add this in, there was a position before I started at Community College of Philadelphia at the University of Pennsylvania, where I had the pleasure of working with both Lisa and Nick in Penn's Summer Science Academy in biomedical research. I ran that program for high school students for a number of years, but also started a tenure track teaching position at Community College of Philadelphia, where I stayed for 11 years. I decided to take the leap into administration and over the bridge to New Jersey, and served as assistant dean in the College of Science and Math at Rowan University. And then while I was at Community College of Philadelphia, I had actually been involved in the Biomedical Technician Training Program, which, as Nick said earlier, is really Wistar's signature education and training program. And so a colleague from the Wistar Institute recruited me over to Wistar to take over that program. I put Jefferson really large over here because Jefferson has also been part of my career throughout these 3 institutions. So Lisa Kozlowski and I wrote a career guidance for trainees grant from the Barrows Welcome Fund, and received that grant. And so we had a program called Mentored Teaching and Health Professional Courses. This was before there was Philadelphia University, the East Falls campus, to provide teaching opportunities for our graduate students and postdocs at Jefferson. And so we wanted to provide that opportunity and had a more of a student-teacher model for that rather than a TA model between Jefferson and Community College of Philadelphia. As an outcome of that grant, in order to make that work sustainable, we developed 2 courses that are still offered and that I still have the pleasure of teaching at Jefferson as an adjunct faculty member, Principles of Pedagogy and Principles of Science Pedagogy. All right, so bringing it out a little bit, since we're at the College of Life Sciences and we can't ignore that we're in this growing life science ecosystem in Philadelphia. So many of you may have traditionally known that our regional economy is referred to as meds and eds. We have over 100 medical centers, colleges, and universities in the greater Philadelphia region. In fact, 1 out of every 6 doctors in the US has done part of their education or training in Philadelphia. And our Philadelphia institutions currently rank 3rd in National Institutes of Health funding. For better or worse, you may have heard the new name Silicon Valley. As Nick also said, we are the home to cell and gene therapy, the first FDA approved cell therapy and gene therapies came about in Philadelphia. And in fact, 80% of pharmaceutical companies have a presence in this region. So at the Wistar Institute, we feel like we sit in a great place as the bridge between the traditional academic institutions in the greater Philadelphia region and our growing biotech and biopharmaceutical industry. So Wistar is a .org. We're not a .edu, but in terms of academic research, we are our nation's first independent biomedical research institute. We became a National Cancer Institute, NCI designated basic cancer center in 1972. And we've held that designation continuously in a competitive renewal process since that time. And one of the things I love about Wistar is how collaborative it is. So 50% of publications are collaborative between one or more Wistar PIs. So we're not a .com, but we're really good at translating basic research discoveries into the clinic. We have a strong technology transfer and business development office led by my friend and colleague, Dr. Heather Steinman, and I'll talk about her a little bit further in the presentation as well. But we are really proud that in the most recent rankings, Wistar ranked in the first percentile in innovation in the world and third in innovation in the US. And so when I came to the Wistar Institute in fall of 2019, the Biomedical Technician Training Program had been running since 2000 as a partnership with the Community College of Philadelphia, the same way as a 2-summer program with 12 students in each cohort. My colleague Bill Werner started this program and had really amazing outcomes. So I don't know if many of you know, but the graduation rate at most community colleges, including the Community College of Philadelphia, hovers around 10%. So we would have 77% of students complete our 2-summer program, and then 46% go on in that first year upon completion to start related employment as laboratory technicians or research assistants, and 64% continue their education. 46 and 64% actually add up to greater than 100%, and that's what we've always thought was the best possible outcome of the Biomedical Technician Training Program. When we have students who are able to get a job in the field that they want to go into and continue their education. So we always like to highlight success stories. And so I picked a beer, Shuda, ahead for this talk. I actually had the pleasure of teaching a beer 3 times, once at Community College of Philadelphia in my undergraduate genetics course, once at Wistar as part of the Biomedical Technician Training Program, and then the last time in my Principles of Science Pedagogy course at Jefferson. She now works at Community College of Philadelphia as a faculty member. So kind of a success story with things coming all the way around. So my vision for coming to Wistar was to build on the success of that Biomedical Technician Training Program by partnering with educational institutions and companies, employing our apprenticeship or learn and earn model to open access for more diverse students, leveraging authentic Wistar research to teach in-demand skills, and securing Wistar's role in the growing Philadelphia life science ecosystem. So I guess my startup package at the Wistar Institute included renovation of space. So the Biomedical Technician Training Program had actually operated out of 100 boxes that came out of storage at Wistar every April and then got packed away at the end of the high school program in July. And so we needed a permanent space in order to expand our portfolio of education and training programs. And so, Jerry, I am your woman if you want to talk about renovating space, because this is an amazing place to work. It actually, I have to watch the PIs at Wistar because they all want to take the space because it's set up like a research laboratory instead of like a classroom laboratory. And that is on purpose, and that's why we call it a training lab. So we really, teach students how to work independently in the lab. We have built-in teaching space. So we let the experiments lead the way. We all know there are wait times. And so we have students start the lab processes, and then we gather them around for just-in-time instruction to really talk about the concepts behind the techniques that they're doing, discuss results, try to teach them how to start troubleshooting. But we make them stand or, maybe a little bit of sitting, but there's no long lectures. This is, truly hands-on learning. And then 3 at a time, we pull them across the hall to our tissue culture room, right? We've got 3 laminar flow hoods, biosafety cabinets, where, we are teaching students how to culture human cells, which is what you need to work in most academic and biotech labs at this point. We do have a little a classroom space that, we use for some other new classes and programs. So when I got to Wistar, I was Associate Dean of Biomedical Studies, and that was in fall of 2019. But Dean of Biomedical Studies, who was the founding Dean of Biomedical Studies at the Wistar Institute, moved toward retirement a little faster. And so I moved up to be Dean in July of 2021. And I got the opportunity to build a dream team in education and training. So the first person I recruited is fellow Jefferson alum, Dr. David Zuzga. David couldn't be here today, but we work really closely. We had led parallel careers. David most recently was chair of biology and integrated science, business and technology at LaSalle University. He was the first person who called me when I moved over to Wistar, and I was the first person. He was the first person I called when I moved up to that dean position to recruit to help me, because we share such a common vision of what we want for our programs. We were also fortunate enough to recruit Kaylee Bice. Kaylee did a bachelor's degree in education, but had worked in a couple of different departments at Wistar, so she is great at our program coordination. And then this past summer, we got to bring Jason Diaz on as our education program coordinator. Jason was David's star faculty member at LaSalle University. And then this January, as we started to be using that training lab more than just in the summer, using it year round, I got to hire a training laboratory coordinator. Andreas Widmer is also a BTT program success story. He completed the program in 2002. Peter, I'm looking at you because he's also Swiss. He came from Switzerland, had been a nurse, but that nursing credential didn't translate from Switzerland. So he started at Community College of Philadelphia, thinking he would, complete a new nursing credential, and found the biomedical technician training program, completed it, was hired by Paul Lieberman at the Wistar Institute, spent 20 years as a research assistant and then lab manager with Paul. And now I don't have to aliquot anymore because I was still doing aliquoting as the dean. I'm also fortunate enough to have the help of an amazing research assistant professor, Ian Teachin. So Ian's currently splitting his time between our education and training programs and research in the lab of Luis Montaner at Wistar. Not under education and training, but essential to our success are some of our PIs at Wistar. So Maureen Murphy is now deputy director of our cancer center. But she is currently the PI of our T32 training grant in cancer biology. This training grant is older than I am. And again, it's something else that it's a testament that it's been successfully renewed every 5 years since 1976. David Weiner is our executive vice president and director of our Vaccine and Immune Therapy Center. He is also the course director of our Vaccine and Immune Therapies course. Dr. Italo Tempera is now our associate director of Cancer Research Career Enhancement in our Cancer Center. He is leading our Cancer Biology PhD program, and passed on from Maureen, Italo and I are now the course co-directors of our Cancer Biology course. And then Alessandro Gardini, who leads our PhD program in collaboration with the University of Bologna, which is the Western world's first university in Italy. So we've had tremendous support to build these resources and the team at the federal, state, and local level. So federally, we've been successful in obtaining grants from the National Science Foundation and the U.S. Economic Development Administration. At the state level, we've been really successful in the PA SMART grant mechanism through the Department of Labor and Industry. Locally, and including some philanthropic donations, we had great support from Philadelphia Works and GSK as part of their 10-year initiative within the Philadelphia STEM Equity Collective to increase the number of Black, Latinx, and women going into STEM careers. So what this means for the Wistar Institute is that after this, spike from the pandemic, we've actually increased our programming while decreasing institute expenses and increased our grant revenues by 2.5 times what it was when I wasn't there. So Karen Award. So I really, purposely chose not to follow the research path because I never, thought I wanted to say I'm the PI or co-PI, but I am currently the PI or co-PI on 10 foundation awards and 6 government grants or contracts. So, so sampling of some of our foundation support and 6 grants or contracts from the government for a total of over $3 million that funded for this work at Wistar at the moment. So I'm going to kind of tell the story of what we're trying to do with lots of our education and training programs to where this work began for me with Wistar with the Biomedical Technician Training Program. So again, I was recruited to Wistar to take over this biomedical technician training program as Dr. Bill Werner was moving toward retirement in his 80s. And, I got to Wistar in fall of 2019. I recruited and selected my first cohort, and they thought they were going to start the program in May of 2020. But we all know what happened in the spring of 2020. And I was devastated about this. I wanted to figure out a way for the students who had been accepted and thought they were starting the program in May of 2020 and finishing it in August of 2021 to still finish that program in August of 2021. So I applied for and received one of the inaugural grants from GSK's Philadelphia STEM Equity Collective to pilot an accelerated biomedical technician training program. So taking our 2 summer program and making it into a 1 summer. So students start with a 2-week lab orientation and then do 2, now 5, but that first summer 6-week lab experiences, 1 in an academic lab and 1 in an industry or core lab. And we had great success, right? So we beat our completion rate 100%, but we also beat the outcomes. So 67% of the students in that 2021 cohort started related employment within the first year, and 92% have continued their education. And so we also applied for and received a National Science Foundation grant from the Advanced Technological Education Program entitled Exceed BTT. Here's a hint: if you're ever applying for NSF money, the better your acronym, the better your chances of receiving that grant. I kid you not. So Exceed BTT, expansion, curriculum, evolution, and enhancement. During that, you also can't say medical with the NSF. All basic science. So biotechnician training. We are in the second year of this 3-year grant, where we are taking our cohort that had been 12 students and going up to 21 students, and going from 1 community college partner to 5 community college partners. And that will really give us more of a regional approach for this program and for workforce development in this region. So the second part is probably my absolute favorite, the curriculum evolution. So the first scientific seminar I attended at Wistar was by one of Maureen Murphy's graduate students. Maureen Murphy, as I said, is our Deputy Director for the Cancer Center at Wistar, and she works on naturally occurring variants of the tumor suppressor P53. And her graduate student was working on this variant that is more common in individuals of African American, and Hispanic descent. And I thought this would be a great project to really engage underrepresented students and also teach, the laboratory skills that are generally applicable, again, in academic and industry labs. So Jeff talked about molecular screening, but those of us who work in wet labs know that all of those predictions and all of those hits have to actually be followed up. And it's usually too much for one lab, one PI, right, to do. So we try to follow up on those hits for Maureen. So as proof of principle, she was able to find a drug, a currently, right, approved treatment, cisplatin, that is actually more effective in treating cancer cells with this S47 variant than the P47 or wild type form. But she's done screens and has a lot of hits. So essentially every cohort of the biomedical technician training program follows up on another of these hits. They learn how to pipette, how to prepare reagents. We do a lot of biomath. We know that that's always tough for everyone from undergraduates to postdocs still. They learn how to extract DNA, PCR, isolate RNA. This is a really tough one to get to work with undergraduates, RT-qPCR. Purify and quantify proteins, run gels of nucleic acids and proteins, follow the SDS page of the protein with Western blotting and detection. Because I can't let go of my favorite laboratory technique of immunocytochemistry. They still do immunocytochemistry. And then we have really increased the amount of time that they spend working in tissue culture, learning mammalian cell culture and assays that are beneficial for Maureen's results. We originally had an ELISA incorporated into this curriculum. But one of the things that we did with Ian Teachin helping us with our program is actually bringing a part of the Montanaire's lab work on HIV research in, so that students are actually, being exposed to two major research areas of Wistar, cancer and infectious disease research. And then the third part of the grant enhancement. So I don't know, Wistar is small. We only have 32 labs. And so we've always used labs at the University of Pennsylvania to help us train our biomedical technician training program students. And then since 2010, we've been sending students to Philadelphia biotech companies, Integral Molecular, and thanks to Nick, Invisible Sentinel. But within the course of this grant, we have also expanded to placing students at Fox Chase Cancer Center and bioanalysis, Century Therapeutics, Ocugen, Amicus Therapeutics, Chimeron Bio, and again, thanks to Nick, Victoria Biotherapeutics. We've had a great outcome. So I talked about the 2021 cohort having 100% completion rate. You got to repeat the experiment 3 times, right? So 2022 also had 100% completion rate. The gray is our historical data. I think that the pandemic has actually affected our percentage of underrepresented and women in our applicant pool at community colleges, but hopefully we'll see that returning to our historical levels soon. But again, we're still following the 2022 cohort, but in the 2021 cohort, they are beating those historical outcomes. And then we don't just send the students out and leave them. And actually, I had a conversation with John Worry when he was the Distinguished Alumni Awardee. And he said, the reason I say yes when you or Bill ask is because you don't just drop the students off and forget about them. You follow up, you check in with the students, you check in with the mentors, and you give the mentors a chance to evaluate the students. So Bill used to do this on pieces of paper, but I brought in, some electronic forms, and the students on a scale of 1 to 5 average between a 4 or 5 on really important laboratory competencies, like, here we go, following and practicing safe lab procedures, using reagents safely, lab equipment safely and appropriately, following and understanding protocols and SOPs, calculating and preparing solutions correctly, planning and setting up experiments properly, performing experiments using technical skills, applying sterile technique and practices, collecting and recording data accurately, maintaining a laboratory notebook, and we are in the process of transitioning from paper to electronic, beginning to analyze data and troubleshoot, communicating results to a supervisor, and demonstrating professionalism in their interactions with colleagues. We also have added a validated tool, the student assessment of their learning gains, undergraduate research student self-assessment, otherwise known as the SALG-URSA. Look, we can do, David and I can still do statistics. We have significant results in student-reported gains in thinking and working like a scientist, personal gains related to research, gains in skills, and gains in students' attitudes and behaviors as a researcher. And then from the 2020 to the 2022 cohort, we have more students agreeing or strongly agreeing that doing research confirmed their interest in their field of study, clarified the field of study that they wanted to pursue. By the way, that's this one disagree, was that student who still doesn't know exactly what they want to do. That the research experience prepared them for advanced coursework, or in red, graduate school. And then really importantly for us, because that was the original concept for the program, that the BTT program prepared them for a job. And so in 2019, Wistar registered the first apprenticeship in biomedical research in the nation. And we just had this program endowed and named the Fox Biomedical Research Technician Apprenticeship, or the BRT. Once we registered that program, we were able to go back and register our biomedical technician training program as a pre-apprenticeship. And so we knew this was effective at training community college students and inspiring them to go on to careers in life sciences. But it was small, right? So we wanted to find a way to increase this program by increasing the number of students we were giving the pre-apprenticeship training to. So our PA Smart grant, this most recent PA Smart grant, has allowed us to expand the program to students at 4-year colleges and universities. And the first 4-year college of university that we actually partnered with is Cheney University. So Cheney is our nation's first historically Black college or university. The students actually from Cheney were the first to use our training lab as part of a biomedical research methods course. They have the opportunity upon successful completion of the course to follow that course with internships, and then also take a life science innovation course. And really all of this is because Cheney is leasing unused laboratory space to startup companies as an incubator, or a thinkubator, as they call it. And so this gives students the opportunity to be able to take our pre-apprenticeship while they're pursuing a bachelor's degree, actually get experience on their campus and at Wistar, and possibly graduate with jobs at those life science companies. David and I were also fortunate. I made him be the PI on this one, and I'm the co-PI on a research experiences for undergraduate site. So these are really prestigious education grants. Some of you might know that education grants, unlike R01s, are not renewable. So you have to come up with new things to do every 2 to 3 to, if you're lucky, 5 years. But this is a mechanism that is renewable, and it allows us to recruit 10 students from across the country for a 10-week summer program at Wistar that starts with our 2-week laboratory orientation before placing students in 8-week internships. And really allows us, and really is designed to support students' pursuit of PhD degrees and help Wistar recruit top graduate students to our programs. So then we asked the question, okay, so if we can take this model, and it's been successful with community college students, and we've expanded it to students at 4-year colleges and universities, can we do it with high school students? Everybody worries, are high school students mature enough for this? So before we did that, we expanded to and underemployed adults who may only have a GED or a high school diploma. So we received a contract from Philadelphia Works to pilot the BTT program for all in Phil, adults living and learning in Philadelphia. We partnered with West Philadelphia Skills Initiative under the University City District, and didn't have prerequisite courses being offered at the community college or 4-year colleges and universities. So we designed our own prerequisite course called Life Science Foundations, and then followed that with a 2-week laboratory orientation in our training lab. And then all students were placed at Iovance Biotherapeutics, a cell-based therapy company at the Navy Yard. And we had amazing results. So a 76% completion rate, so about what that original biomedical technician training program for community college students achieved. And 77% have started related employment with full-time positions with possibly just a GED or high school diploma, starting at $23 an hour to essentially do human cell culture work. We've received a lot of positive press for this work, as well as our other education and training programs. This was, a big honor for us to win the BioBuzz Workforce Champion Award. And I know Nick's looking at his watch, so I'm trying to hurry up here. But Wistar had always had programs for high school students, undergraduate students, graduate students, and postdoctoral fellows. But really what I've done is bring these all under one umbrella. We've had a high school summer fellowship program where that having experience running Penn's program has come in handy. We have also always been very responsive. We have lots of class and schools come, including Greg's cell biology class from Rowan, come to Wistar. I mentioned our biomedical technician training program, a registered pre-apprenticeship that leads into our Fox Biomedical Research Technician Apprenticeship. And then when he was at LaSalle, David Zuzga developed that life science innovation course with Heather Steinman at the Wistar Institute. I'll let him talk about that when he someday gets a Distinguished Alumni Award. At Cheney University, we offer that biomedical research methods course where with an internship can also qualify as a pre-apprenticeship. And then this year, David ran the course with students from LaSalle and Cheney University. We are also registering our second apprenticeship in quality science. So if you've looked at any of the workforce reports in our region, laboratory technician is the most in-demand position. And then also in the top three are quality science positions. And quality science has always been a role that has been occupied by individuals at various levels, from high school diplomas to PhDs. So we are registering our second apprenticeship. I talked about that BTT program for all and fill as an expansion of the BTT program, and then our programs for students at four-year colleges and universities. We have always had students doing their thesis with Wistar faculty. And as I said, we teach two really popular courses in cancer biology and vaccines and immune therapy for students at the University of Pennsylvania, where both undergraduate students and postdoctoral fellows can sit in. We currently have a cancer biology PhD program that started in 2011 with the University of the Sciences and is currently under St. Joseph's University. And then I talked about that new PhD program with the University of Bologna. We feel like we offer an amazing training program to our postdoctoral fellows. So I've learned a lot from Lisa Kozlowski over the years, and the co-curriculum falls under us in education and training. With responsible conduct of research and rigor and reproducibility. We also include the students from the University of Bologna. And then since last year, we've also offered a section of life science innovation for our graduate students and postdoctoral fellows. I chair our training committee to look after these graduate students and postdocs at Wistar, and I also advise our Wistar Trainee Association as a former president of the Graduate Student Association. This is near and dear to my heart. And in green, I've just highlighted the expansions in the portfolio since I started as dean at Wistar. So, supporting the pipeline. Historically, Wistar had a really small program for high school students and a large number of postdoctoral fellows. And in 2022, our numbers all looked about even. What we really want to do is invert and have more high school students and undergraduate students that we connect with. But Sue will appreciate that I couldn't show that reverse pyramid to Wistar PIs because they would say, oh my God, we can't have less postdocs. So we're not trying to decrease the number of postdocs, but we're trying to increase the number of high school students and undergraduate students that we work with in order to be able to have graduate students and postdoctoral fellows who know and want to come back to the Wistar Institute. So my future plans, again, since my days of science, I've always been more interested in the next generation. So I want to effectively train the next generation of scientists by partnering with additional educational institutions and companies, employing innovative models to open access to the experiential learning that we need for more and more diverse students to be successful in STEM careers. I love leveraging authentic biomedical research to teach in-demand skills. So we all know that consumables are expensive. I literally can't spend money if it's not actually serving another purpose. I don't want to just have a student do a PCR to teach them a PCR. I want there to be a purpose for them to do that PCR. And our dream is for Maureen to publish a paper that has tens or even 100 student co-authors. And then, really taking a leadership role in the growing Philadelphia life science ecosystem. So with that, I am going to call out a couple of people on this long list of acknowledgements. Some of you know that I had not the best mentor as a graduate student at Jefferson. But Derry Altieri, the president and CEO of the Wistar Institute, has been an amazing mentor and boss to me at Wistar. He still has an active research lab, and this is still why I teach as a dean. This is one of the things that makes Wistar such a special place, is that it's an institute really for and run by scientists. Dario leads by example every day. He runs the institute like a lab. So if you loved those lab meetings and you still feel like you need a PI in your life, Wistar is the place to be. And even in administration, there are a number of us that have PhD research training. Brian Keith was the founding dean of biomedical studies, and I talked about Bill Werner, who had the foresight to start the biomedical technician training program with Community College of Philadelphia back in 2000. So I am indebted to them. I talked about some of the people in our current education and training team, but really it's a research institute, but all of the Wistar faculty are mentoring students and postdoctoral fellows. All of our core facilities are always happy to bring students in on tours, and I am thankful for that support. Again, it takes a village to do this work, so lots of great administrative support at Wistar, and then from our partners in academia and industry, and then some of these intermediary organizations. Okay, and so a special thank you. I can't say enough great things about Jerry, Lisa, and Carol Beck. I am happy that as an adjunct, I get to call them my colleagues, but they are always the first person to congratulate me on successes, and some of the first emails and calls I make during those challenging times. Karen Schindler, I talked about other fellow Jefferson alum from my lab, Melanie Westcott and Aaron Elliott. I talked about David, some other, really great friends at Jefferson who I continue to collaborate with in different ways, including Kelly McCorkle, who's back at Jefferson. Special thank you to Nick Siciliano and Adam Snook for being sincerely the best scientists I know, and amazing friends who are, again, always happy to help and contribute. I was actually nominated for this award by Marianne Wagner-Graham, who wasn't a fellow Jefferson alum until we merged with Philadelphia University, which is where she went for her undergraduate. We won't talk about that. She went to Hahnemann Drexel for her PhD. But Marianne and I worked together at Community College of Philadelphia. Went through some challenging times, and I am thankful for that nomination. And then Lisa Ambrose Lancy, who I mentioned, we worked together as part of the Penn Summer Science Academy, and I was pleased to be able to receive this news from her. My husband Bernie came in, so I can't thank him and our daughter Mairead enough. This isn't a picture from one of the Jefferson alumni days at the Phillies game, but this is one of the things we like to do as a family, as well as go to Hershey Park. Special thank yous to both of them. Again, they're the first people to celebrate my successes, but also there when mommy is stressed with things like grant deadlines. Jeff talked about applying skills from our PhDs into our careers, but I would also like to just brag for a minute and say that I am the best youth sports manager as a volunteer for my daughter's soccer and softball teams, but Bernie does a lot of coaching, and I am the behind the scenes scheduler and communicator with parents and players. And this is, one of our favorite things to do is watch our daughter in her sports events. So I know that we're going to save questions for the fireside chat, but some things that really keep me motivated are what the students in our programs have said. And so, again, I talked about Abir as an example of a student who I've had at different points in her education, but really, down here, having students who go on to become teachers is also a great sense of pride that I've been able to do in my career. So thank you for this award.
Thank you, Kristy, for that very inspiring talk. And I'll take this brief moment to plug her work. So again, you can see from the statistics the impact that Kristy's work leading and now pioneering some of these programs have. But I can tell you from personal experience that it's really impactful to, help a person. So we've had the pleasure of mentoring some of those students and watching them go on into careers in science. So I would encourage our fellow alumni, faculty, if you guys can participate in some of these programs and take your students, I would assure you it's super rewarding. Okay, so now we're going to transition to a little bit of a panel. I've given our guests an opportunity to interact with the awardees. And it is my distinct pleasure to introduce Dr. Sue Dillon, fellow alumni, and so also a friend who will moderate the panel, for us today. Sue is the current CEO and co-founder of Arrow Biotherapy here in Philadelphia. Prior to Arrow, Sue held multiple leadership roles at Centocor, Janssen, including the global therapeutic area head for immunology R&D at Janssen, where she led the clinical development of a series of blockbuster drugs, including Remicade, Simponi, and Stelara. As I mentioned, she earned her PhD here and was also the 2007 Distinguished Alumni Award. In 2013, and this is really impactful, Sue was selected by Fierce Biotech as one of the top women in biotech. And I couldn't agree more with that. So really happy to have you, Sue. I know personally how busy you are. So, really appreciate you taking the time and spend a little bit of time with our awardees today. So I'd like to invite our awardees up and invite Sue up and open up the panel discussion. Again, this was meant to be engaging, so I really encourage the audience to ask questions of our awardees. And I'll turn it over to you, Sue.
Thanks very much. Can you all hear me?
Yes.
Good. No mic.
Wow.
Hey, yeah. Okay. Okay. So first, I just want to congratulate again Dr. Jeff Sanders, Dr. Peter Rohner, and Dr. Kristy Shuda McGuire. It's very, very inspirational seminars from both of you. And thought that maybe we could just start off by taking from all your career experience to today. There's so much happening in science across the board, and hear from each of you as what you think are the real drivers of innovation today. And I guess I'll start with Jeff since he's right here.
First in line. So I would say, from my perspective, how we've operated, right, as a society, and I'll harp back to sustainability. And I think everyone in the room probably has heard sustainability more come up, right? We need to think about taking existing processes and making them greener, because it's very important, not only for the environment, but also, right, there's ethics involved. There's a whole host of reasons, but importantly, trying to modernize some existing processes. Make R&D, in fact, more sustainable. There are some things that we'll never get away from. There are plastics that need to be used in research, but areas where we can make things more sustainable, more friendly, is a key driver, for on a planet in 50 years.
That's it. Dr. Rohner, you've had a long and distinguished career in biochemistry, and there's been a revolution in the last so many years, molecular biology and deep understanding of, we've kind of gone from the biochemistry I memorized as a graduate student to understanding a lot more of how that relates to disease. So maybe you could point out what you think are some of the seminal discoveries recently and what you're excited about.
Yeah, I think this is a very difficult question to answer, actually. But it is pretty amazing. I mean, I have some colleagues who are just 1 or 2 years older. And, they had polio, for instance. I was lucky enough to, as a very young child, to be immunized against polio. An old but very important step. In biochemistry, I started my first experiments when we did an assay, always calculated the standard curve. Well, the revolution was to use a computer that actually calculated the straight line that would go through that. I had a faculty member in analytical chemistry who kind of flashed his pocket calculator by Hewlett-Packard that at the time cost way over $1,000 and land on the moon with something like that almost. We didn't really have any PCR, of course, and so on. I think it is very difficult to say you want to go someplace and use innovation. I mean, at that time, membrane biochemistry was the sexy thing. And everybody thought that what's the problem with cancer, we can solve it soon, of course, is that cells don't have this contact inhibition anymore. It must have something to do with the membrane. Nobody thought it would have anything to do with genetics, that it's actually a disease of the genome. And so, I think it is very difficult to make directed discoveries, to predict something. I mean, we have CRISPR because some basic people looked at bacteria. We have PCR for the same reason. And I guess I'm excited about, at this stage, probably about medical discovery. What gets us eventually to maybe treat Alzheimer?
So I think for me, the key to innovation right now is working interdisciplinarily. So I really enjoyed Jeff's talk and multidisciplinary. So again, I talked about that 50% of the publications that come out of the Wistar Institute are collaborative between more than one lab. So I don't know if the grad students, the alumni who are here can think about what their papers look like, but there is more of an impetus that, you need to work across disciplines to really be able to make those advances.
So something that strikes me also when I listen to your presentations is how important it is that general populace understands something about science today. And it's gotten more and more and more sophisticated. It's bringing us more and more medicines, new materials, everything else. But it's scary in a way to think that on the one hand, you see a kid who's 2 years old playing with an iPad and knowing exactly how to use it and swiping, right? And on the other hand, people don't understand the first thing about what is a vaccine and why should I take it? So I'm just curious in your different lines, first of all, what do you see as barriers to science advancing? And is that a big challenge? Getting people who aren't trained, we all are as PhDs, and appreciate the basics and how they translate into meaningful, whether it's medicines or discoveries or products, whatever. How do we sort of rise to that challenge, and what other barriers do you see to innovation? Start the other end this time with this.
Sure. So actually, I will take any ideas for this because this is something we've been struggling with in our education and training programs that we want to be able to measure, right? But if you think about that, many of our students are first generation, definitely first generation into science and healthcare. How is opening up science to those individuals, going to be able to have an impact in terms of improved healthcare. So, you know, that's
do this and I need this because it helps me solve a problem, not I'm doing quantum mechanical calculations to get spectroscopic properties from something I put in as a replacement food dye.
Right.
Those are very different ways of communicating, but they're still achieving the same goal at the end of the day.
Right.
So for me, and to steal and sort of piggyback off of both their responses, I think there needs to be a sense of transparency, and I would say interpretability, but that kind of feeds back into what I'll say relatability. We need to be able to communicate things in a way that people understand outside of a general, like your level of expertise. You have jargon, you have, processes and frameworks. If you want people to understand that, respect it, and accept it as a truth, you need to make it relatable. And I think that the transparency part is we hide behind the jargons, we use the words, the things, and we overcomplicate it. There's very, very easy ways to describe complex processes. And I think as scientists, we need to do a better job of being effective communicators in that way. People will believe us more if we don't hide behind things that the first person up front can't explain very well, like vaccines, not them saying that that's what happened. But if you can make it relatable and then people get behind the idea, we're not being disingenuous, we're not necessarily not giving the full truth. We're just making it so that it's digestible. The same way as you don't teach a kid calculus, you teach a kid 1 + 1.
You make me wonder if part of the PhD program should be effective communication. I remember we trained arduously. I'm sure you all remember giving your first seminar, but that was to a scientific audience. We should probably be training scientists on how to give a great talk to a non-scientific audience, and that would be a real service. I just listen and see if people have questions before I go on with questions. If you had any questions after listening to the presentations today.
Thank you, Sue, and thank you, everybody, for the great discussion. So continuing on that theme, perhaps, since we're, of course, here institutionally concerned with education and training. So I wonder, with the pace, talking about innovation, the pace of change, there's always more and more and more and more to know, more to read, more to try to understand. What do you see in any of your spheres as the role of carving out time for historical perspective. Meaning, in other words, the process of discovery, some would argue, I don't agree, but some would say big questions have been answered. We discovered DNA once we are, now we have it. Yes, we can argue about that. So I wonder, given how little time there is in a course, in a program to do what you need to do, what role do you see in education and training for finding the time or going back and wherever you would start and giving it that historical perspective so the growth of concepts and technological discovery is grounded in some of the real foundations of biomedical science?
Can I answer that? I think it's really important. Just from what Dr. Roner said a minute ago, that looking at cancer cells and they don't have normal contact inhibition, that was thought to be the problem until later it was realized that it's genetics, and genetics is one of the many phenotypic changes is that contact inhibition, but it starts with the genes. I thought that was fascinating. I had never thought about that way. And I think it could help the students to look at whatever their projects are and almost, encourage them to take a step back in the way that they look at things, not just, monolithic. So I think it would be really, really, really helpful.
I would add to that. I think the historical perspectives are very important, provided you teach about the failures. Read a paper, when we look at a textbook, we're looking at the combined knowledge of a bunch of individuals who got it right and only showed you the part that they got right. Whereas the vast majority of what we do are failures, right? And that failure is the greatest teacher. I am a firm believer in that. That's how you learn, that's how you grow. And I think you do need to teach history because you're doomed to repeat it if you don't, and people will waste time, energy, and government money to do the same mistakes twice. Teach the failures, teach the successes, keep it well-rounded, and teach people that it's okay to fail. They're going to.
I'm just going to tell a funny anecdote of working with Adam and Nick to try to develop a kit for teaching molecular cloning. And I actually said to them, it's better if it fails because the students learn more when they have to troubleshoot and think about that. So they were like, sweet, this is the best business idea ever. That's very cool. It has to work at least one time to show them what the expected results are. But I just wanted to talk about this Life Science Foundations course that David Zuzga and I developed for a prerequisite course for those adults who may only have a high school education. And it's really, instead of telling them that DNA is genetic material, it's literally presenting them with the results from Griffith and having them tell us and do that analysis. So it's teaching the historical, but through the same processes that we want students to be able to, look at data and figure out what's going on. So I think there's a way to do it. We just have to, again, make the teaching more like the learning that happens when you're doing research.
Okay, so I'm going to switch to a more not a scientific topic, but what does a typical day look like?
Mine's the most boring, probably. Meetings. I'm not traveling, so I participate in a lot of conferences, talk to a lot of people. Of course, when you're a company, you have customers, you have, collaborators, things like that. So there's always a lot of communication. And then there's also a lot of managing. When you're doing research, but also making a commercial product and providing feedback, you're doing work, you're figuring out if I'm doing the science right. If it's failing, is it failing for technical or engineering reasons, or is it failing for actual scientific reasons? And so then I get to spend maybe a third of my day working on that, and then managing, those that are working on this from a full-time perspective, because they may not be. It's almost like a postdoc or grad student where they're excellent scientists in their own right, but they're doing the work, running the simulations, analyzing, but they don't get the larger context. So then there's this sense of tying things back together. And then if you mix and match all of that, then that's probably an average day.
Dr. Roman?
Yeah, so I'm at 30% now only, but I will relate to what I do when I'm 100% or when I was 100%. It takes an amazing amount of time to give a 50-minute lecture. So prepare a new one. I'm lucky, it takes me 1 week. If I'm unlucky, it may take me 3 weeks. It's also amazing when you have only 10 students, you can kind of find your way through it. You don't have to be perfect. If you have 270 students, as we have medical students here, there has to be a level of perfection that's much higher, because otherwise suddenly have a group of students that kind of get together and say, well, this is terrible. And then they pull everybody else into it. So it's a very dangerous equilibrium. I have to say, so a lot of time, obviously, when you develop a lecture goes into just reading research, trying to make sure that you understand what's going on. And you have to kind of reframe it and wonder, can you tell it to somebody who does not know this and who is experienced in teaching something? What also comes in, you get to know where people have trouble. And it is very important to kind of use that to make one's lesson or whatever it is better. I love to do the slides. It's something that's more artistic. And that's a whole science in itself. Then you have to practice, of course. And what amazed me is that when you've been teaching a long time, I think that must be the same if you're a researcher full time, you actually get much better at presenting. And you need a little bit less time presenting it. And sometimes when you're in an emergency, you just go into automatic mode. And it's not going to be absolutely terrible as it would have been when you started out as a graduate student. And then we have lots of meetings. The education of medical students is extremely collaborative at this point. You know, and only collaborate by me.
All of you would have anxiety if you looked at my email inbox right now. So I think email is, you know, where most of my time gets spent, and then lots of meetings. And then I love teaching, but I can't devote that time to preparing lectures. So my preferred teaching method is, you know, jumping right in with the students in lab. I think, you know, you just said how medical education has become more collaborative. You know, all of our graduate students and alums, if you think about where you learned the most, was it sitting in this room for cell biology or what's become GC 550, right? Or was it in your labs? And so how do we turn that modern learning experience to be more effective so that, you know, our faculty aren't spending hours and hours and hours preparing and delivering lectures where students are only going to, you know, retain 10% of the material and then, you know, possibly be able to use and apply even less. So, you know, while I will never throw out the baby with the bathwater, and I believe, you know, we all need a strong foundation in biology, chemistry, physics. I'm going to argue at this point, computer science, for all of our STEM careers. I think it, you know, those experiential learning experiential learning opportunities are just so much more effective.
So each of you have had amazing careers that have taken some twists and turns that you probably couldn't have predicted when you first showed up at Jefferson, right? Whether that was a lifelong career as a professor teaching students and doing research or moving out into industry or into science education and all those amazing programs. I didn't know about half of them at the Wistar. So I'm sure that there were challenges along the way, many, and it would probably be helpful to the audience to hear about one of those, at least, that was a really significant challenge, and what you did, or how did you overcome, circumvent, or deal with that challenge? So I will start the other end this time.
And full disclosure, my graduate advisor is no longer at Wistar, so I no longer at Jefferson. So I not a current Jefferson faculty member. But I did not have a good thesis advisor. I had an even worse department head at my first academic position, and now I've really flourished under good mentorship at the Wistar Institute. So the importance of mentoring and training people to do that mentoring, and also on the other side, right? Like I also learned throughout my career, because I just thought those were things that were happening to me, but to actually train mentees to be more proactive about what they need. So that's something that we're trying to incorporate more of at Wistar, is both training the students and postdocs to be better mentees and advocate for their needs, and then also training the faculty to be better mentors during those experiential learning.
Dr. Roner?
Yeah, I'm not sure what to pick, but I'll pick writing my biochemistry textbook. So this was to be for medical students and pharmacy students. Medical biochemistry, surprisingly, is quite different from biochemistry graduate students have to know. I mean, a physician does not have to know how to calibrate the pH meter, for instance. So I started out, I think, around 2003 or so. The editor who got me started, and the idea was to use the images of Miller, who was a physician, a medical illustrator, and use this for a variety of topics, including biochemistry. So I was going to be the person of biochemistry. This editor found me a collaborator, and the two of us went back and forth probably for about 10 years, trying to write our 40 chapters. And we said, okay, sorry. Initially, it was thought that it would take us 2 or 3 years. So we were pretty much done. We said, okay, almost done. And we submitted. So they said, no, right now, we don't want to have any new books anymore. So we were too slow. There was all that work kind of just sitting there. And then maybe 3 years later, the editor contacted me, said, would you be interested or willing to finish this in a year or so? I said, holy smokes. Well, I called my collaborator. He said, no, I'm sorry, I'm done with this. I'm retiring. I don't want to have anything to do with it. So I just sat down. I tried to use absolutely every hour from early morning until late at night. Somehow magically, it more or less happened. Torture.
And so the book has been published?
It's been published. The official copyright year is 2018, but it's 2017.
That's great.
Oh, okay. So since I started in life science, and even my first part of my career for 2 years was life science portion of Schrödinger, which is known as a life science primal, right? We now own that. So most people are familiar that we're a life science company. When I transitioned really into materials, is starting to interact with customers and scientists that have 20, 30, 40-year careers doing this. You have to know enough to be able to sound smart, or at least that you can carry on a conversation. So my boss very early on told me, well, you're not a material scientist, you're a life science person. And that probably made me mad at the time. But, I came in with a unique perspective. I didn't have any of the preconceived notions, prejudices of being trained as a material science. I was trained here. really in an interdisciplinary sense. So I read, and then I talked to people. I was honest about things I didn't know. And I think that really helped me to a point where I no longer cared about what I was called. And then one day my boss casually was like, "Oh yeah, you're a material scientist," or something like that. And I went, "Yeah, and by then it didn't matter. I mean, may, have been frustrating at first, but the fact that I didn't care and figured I'm just going to solve the problem and I'm going to understand and have a conversation was, a big, I think, a challenge to overcome, because you usually have to learn a whole new set of fields too, not just one. And the grand irony of now everything being made with biomaterials and it driving it right back to life science is a grand irony that's not lost on me. But it really, going and learning something else while also trying to work for a company that needs to make money is challenging. But I think it was really rewarding, and it does help me because I do bring a unique perspective sometimes.
Sure. Yeah.
Sometimes.
So I have one last question for all of you, but before that, is anything else from the audience?
Yeah, I have a question from one of our Zoom attendees who apparently can't get in through the chat. So it's Dr. Thomas Knudsen, who is an alumnus here from Jefferson, in fact, a former recipient of the Distinguished Alumni Award, and also a board member. And so he wanted you to comment on the role of collaboration between industry, government, academic sectors to synergize biomedical innovation.
Sure. The tough science is academics are always going to be one solving the real challenging problems. They have the time, the energy, and the resources to focus on it. How does that actually ever get used beyond publishing a paper and continue to get grant money is sometimes a question. And I think if we could have more academics seeing how their work actually translates, not just translational science and that you end up with therapeutic and you help treatment for cancer, but what are the long-term, how are people using it on a regular basis? I think that is something that we don't do a very good job of, that we should be doing a better job of, is really seeing idea, research, original research through, if it's applied or not, where does it actually take you? Because I think that is not only rewarding and encouraging, but much like your textbook, right? It also helps the next person, educating at the same time.
I agree, but I don't think I can add anything meaningful here.
I mean, we all need each other, right? We need, this is a puzzle that has to come together in order to bring things right from bench to bedside. I think not only, just because each sector, but each part play a role. I think, more often now those lines are blurring. And that's a good thing for the innovation that comes out.
Going along with what each of you have said, I think basic science is going to come from the universities. It's generally not coming from industry. Industry is more applied and takes things from the bench to some product. That's always the goal. So by definition, it's more applied. But in doing that, discoveries are made. So it is a circle. It isn't a one-way street that just kind of ends. The information that happens, whether it's developing a drug or a new product, whatever, is also very important science that's published in the academic journals and all of that. So that then comes back into the institutions that teach and do research. And so I think it's a symbiotic ecosystem, as people use that word. And it's very, very important because each are specialized. And you're not going to find a tremendous amount of product development in academia, and you're not going to find a tremendous amount of basic research in industry. It's not the nature of the business. So it's important to have the dialogue back and forth. So my last question for the panel is, I'm going to deviate from our script here. So my last question for the panel is, if you could say in one or two sentences, what was it about your education at Jefferson or your time as a professor at Jefferson that has made a big difference for you in your careers and in your life? Start with you, Jeff.
All right.
So Jeff was looking to the other.
Yeah, I was trying to skip that one.
I got one.
And you can't talk for 10 minutes because we're all.
No. I never
One thing.
keep people from food or beverage. So having a supportive advisor was probably one of the most impactful things. Someone that gave me the freedom to grow. Having someone that believes in you and gives you the responsibility was probably, I think, one of the best parts about being here in Jefferson. And I think that's a culture that's cultivated really well here.
I think what I appreciated the most was that it was relatively easy as a basic science person to interact with physicians and get their advice, especially, when you're teaching medical students, you can't teach them their graduate biochemistry. Biochemistry, they have to know as physicians. So that's one thing. Jefferson has a great tradition of teaching and hearing about teaching. I think that's the other part. And I'm really also happy about is my colleagues in my department have really nice atmosphere. That can really make your day.
I think for undergraduates and graduate students, the most important thing they learn at Jefferson is to learn how to learn, right? Because we've all said that things have already changed, even in Jeff, who's got the shortest careers, the Young Alumni Award winner, but how quickly innovation has been happening. And that's why I'm most proud that in our workforce development programs at Wistar, that we see students continuing their education, right? So teaching students how to learn, and the fact that they're, this is part of what science means, is that you're going to need to, but also that you get to continue to learn throughout your career.
And I can echo what each of you said, even going back further from when I was here at Jefferson. A lot of those same things definitely read through. Very supportive environment, great mentor, very challenging academically, but really prepared me. The best thing was doggedly learning how to read the literature and understand it and present science. That was the big deal. Okay, well, thank you very much.
Thanks to our awardees for a great panel. Just a couple of brief parting remarks before I invite everyone to join us at the Alumni Center for some food and beverages. I think one of the kind of ongoing themes, around the alumni board, and this event in general, is just this theme of kind of giving. And it was Kristy actually that encouraged me to get involved with the alumni board to begin with. And at the end of the day, what we've tried to, inspire among the group is really engagement and giving back to our students, giving back to our fellow alumni, giving back to the faculty and the staff here at the college and university. And I just want to encourage all of you to get more involved and to continue to do that, because I think that's, especially with the growing student body, we have a unique perspective as alumni. We all have our career experience to be able to share and give back. And look, it's been really rewarding for me to be able to do that, not only here, but even professionally, where I've had this great fortune of being in a position to be able to mentor people. The other thing that's really great is you never stop being mentored. On that note, I'd like to thank some of the people that supported me, including the faculty and staff here. The dean has been very supportive. I'd like to thank Lisa Kozlowski, who's been an integral part of the board and the activities. I'd like to thank some of our past presidents, Dr. Elaine Francis, Dr. Michael Black. I think I saw Johnny here as well. They really mentored me in how to help shepherd the alumni board and our initiatives forward. So thanks to everybody for your time today, for participating. I look forward to networking with you a bit over some food and drinks. And thanks for a great alumni day.